Bismillah ar-Rahman ar-Rahim. A sequence of random variables, S1, S2, S3, and so on, is called a martingale if each has a finite absolute first moment, and if the conditional expectation of Sn given the random variables from S1 to Sn minus 1 is equal to Sn minus 1. Here is an example for a martingale. Consider the random variables y1, y2, and so on. Those are zero mean and are independent and identically distributed. Sn is equal to summation k from 1 to n yk. The sequence Sn is a martingale. To check this, note that Sn has a mean of 0 for every positive integer n. The conditional expectation of Sn given the random variables from S1 to Sn minus 1 is equal to the conditional expectation of Sn given the random variables from y1 to yn minus 1. Note that S1 is equal to y1, S2 is equal to y1 plus y2, S3 is y1 plus y2 plus y3. If we collect the random variables from S1 to Sn in an n-dimensional vector, the random variables from y1 to yn in another n-dimensional vector, these two vectors are related via the following lower triangular matrix. Note that this matrix is invertible. The determinant is the product of the elements on the main diagonal, which is 1. There is a bijective map between the s vector and the y vector. If we know those random variables from S1 to Sn minus 1, we know exactly what are the random variables from y1 to yn minus 1 and vice versa. Sn is written here explicitly as the sum. Now, when we take the expectation, we are conditioning on those n minus 1 random variables. These are constants when we take the conditional expectation. Yn is zero mean, yn is independent of these random variables. So this expectation is equal to 0. We are left with this summation here. This is nothing but Sn minus 1. The expectation of Sn given the random variables from S1 to Sn minus 1 is Sn minus 1. This sequence satisfies the definition of a martingale. For a sequence to be a submartingale, we need a finite first absolute moment, and we need the conditional expectation given the random variables from S1 to Sn minus 1 to be greater than or equal to Sn minus 1 for every n greater than or equal to 2. By definition, every martingale is a submartingale. Let's take the expectation of both sides with respect to the random variables from S1 to Sn minus 1. On the right-hand side, we end up with the expectation of Sn minus 1. On the left-hand side, by the Tower rule or the law of iterated expectations, we get the expected value of Sn. This law states that the expectation over y of the expectation of x given y is equal to the expectation of x. For a submartingale, we have the expectation of Sn greater than or equal to the expectation of Sn minus 1. For a martingale, we have an equality sign here, and so we have the expectation of Sn equal to the expectation of Sn minus 1. On the previous page, we took the expectation with respect to the random variables from S1 to Sn minus 1. Now, we take the conditional expectation of both sides with respect to Sn minus 1 given the random variables from S1 to Sn minus 2. On the right-hand side, we get the conditional expectation of Sn minus 1 given the random variables from S1 to Sn minus 2. From the definition of a submartingale, this expectation is greater than or equal to Sn minus 2. On the left-hand side, we started with this expectation, which is the conditional expectation of Sn given the random variables from S1 to Sn minus 1. Now we are taking the conditional expectation with respect to Sn minus 1 given the random variables from S1 to Sn minus 2. By the law of iterated expectations, we get the expectation of Sn given the random variables from S1 to Sn minus 2. If our random variables are absolutely continuous, they have a PDF, a probability density function. This expectation here is the integral of Sn multiplied by the conditional PDF of Sn given the random variables from S1 to Sn minus 1. Taking the expectation with respect to Sn minus 1 given the random variables from S1 to Sn minus 2 means that we take this integral, we multiply by the conditional PDF of Sn minus 1 given the random variables from S1 to Sn minus 2, and then we integrate with respect to Sn minus 1. By the chain rule, the product of these two probability density functions is the conditional PDF of Sn and Sn minus 1 given the random variables from S1 to Sn minus 2. When we integrate with respect to Sn minus 1, we get the conditional PDF of Sn given the random variables from Sn to Sn minus 2. Lastly, we multiply this PDF by Sn and integrate with respect to Sn. When we do so, we get this expectation here. The main definition of a submartingale has the inequality that the expectation of Sn given the random variables from S1 to Sn minus 1, this is greater than or equal to Sn minus 1. From this definition, we have concluded that if we take the conditional expectation of Sn given the random variables from S1 to Sn minus 2, this conditional expectation is greater than or equal to Sn minus 2. Starting from this inequality, we can take the conditional expectation of both sides with respect to Sn minus 2 given the random variables from S1 to Sn minus 3. And we get this inequality here, that the conditional expectation of Sn given the random variables from S1 to Sn minus 3 is greater than or equal to Sn minus 3. Repeating this procedure, we obtain the following result. The conditional expectation of Sn given the random variables from S1 to Sn minus m is greater than or equal to Sn minus m. This is true for m equal to 1, 2, all the way to n minus 1. For martingales, this inequality becomes inequality. Suppose that this sequence is a martingale. This means that the expectation of the absolute value of S of n is finite for every positive integer n, and the expectation of Sn given the random variables from S1 to Sn minus 1, because we have a martingale, this conditional expectation is equal to Sn minus 1. Function h is a convex function. Suppose that the expected value of the absolute value of h of Sn is finite for every positive integer n. Then this sequence, h of S1, h of S2, h of S3, and so on, is a submartingale. Let xn be h of Sn. To check that the sequence xn is a submartingale, we need to check the conditional expectation of xn given the random variables from x1 to xn minus 1. We should be able to prove that this conditional expectation is greater than or equal to xn minus 1. However, we do our proof in two steps. In the first step, we take the conditional expectation of xn given the random variables from S1 to Sn minus 1. We condition on the S random variables, not the X random variables. And the reason for doing this is that we need to exploit the given information that the S sequence is a martingale. The conditional expectation of xn given the random variables from S1 to Sn minus 1 is equal to the conditional expectation of the convex function h applied to Sn given the random variables from S1 to Sn minus 1. Because h is a convex function, we can apply Jensen's inequality. This conditional expectation is greater than or equal to the convex function h applied to the conditional expectation of Sn given the random variables from S1 to Sn minus 1. Because this sequence is a martingale, this conditional expectation is exactly equal to S of n minus 1. And this is x of n minus 1. Using Jensen's inequality, this conditional expectation is greater than or equal to x of n minus 1. To prove that the sequence of x random variables is a submartingale, we need to condition here on the random variables from x1 to xn minus 1. So we are not done yet. The left-hand side here is the conditional expectation of xn given the random variables from s1 to sn minus 1 and from x1 to xn minus 1. Note that if we know s1, then we know x1. If we know s2, then we know x2. If we know Sn minus 1, we know Xn minus 1. Now we take the conditional expectation of this quantity here and Xn minus 1 with respect to the random variables from S1 to Sn minus 1, conditioned on the random variables from X1 to Xn minus 1. Because we are conditioning on Xn minus 1, the conditional expectation of Xn minus 1 is itself, by the law of iterated expectations, this is the conditional expectation of xn given the random variables from x1 to xn minus 1. If the random variables are continuous, this expectation here is the integral of xn times the conditional PDF of xn given the random variables from s1 to sn minus 1 and from x1 to xn minus 1. What we do is that we multiply by the conditional PDF of the random variables from s1 to sn minus 1 given the random variables from x1 to xn minus 1. We integrate with respect to these random variables. The product of these two PDFs is the joint conditional distribution of xn and the random variables from s1 to sn minus 1 given the random variables from x1 to xn minus 1. When we integrate with respect to these random variables, we end up with the conditional PDF of xn given the random variables from x1 to xn minus 1. Bringing this xn here and integrating with respect to xn, we get the conditional expectation of xn given the random variables from x1 to xn minus 1. Note that using the law of iterated expectations, or if our random variables are continuous, interchanging the order of integrals, all these are justified by the assumption that we have finite first moments. Since we proved this inequality here, then indeed the sequence x1, x2, x3, and so on is a submartingale. The stop process can be defined as follows. J is a stopping time with respect to the sequence Sn. Here, J is a positive integer. Sn bar is equal to Sn if n is less than or equal to J. If n is greater than J, Sn bar is equal to Sj. This can be written as Sn indicator n less than or equal to J. The indicator function is 1 if the condition inside is satisfied, 0 otherwise. To take care of this part here, we add summation m from 1 to n minus 1. Note that m is strictly less than n. Sm indicator J equal to m. If Sn is a submartingale, Sn bar is a submartingale. The first step is to show that Sn bar has a finite first absolute moment. We can use the triangle inequality to upper bound the absolute value of Sn bar by the absolute value of Sn, indicator n less than or equal to J, plus summation m from 1 to n minus 1, the absolute value of m, indicator J equal to m. The indicators can be upper bounded by 1. We get that the absolute value of Sn bar is less than or equal to summation m from 1 to n, the absolute value of Sm. Taking the expectation of both sides and making use of the fact that expectation is linear, the expectation of the absolute value of Sn bar is less than or equal to summation m from 1 to n, the expectation of the absolute value of Sm. These expectations are finite, and we have a finite number of terms. This absolute first moment is finite for every n. To show that Sn bar is a submartingale, we need to study the conditional expectation of Sn bar given the random variables from S1 bar to Sn minus 1 bar. For the process Sn bar to be a submartingale, this expectation must be greater than or equal to Sn minus 1 bar. But like what we did on the previous page, we start our investigation using the conditional expectation of Sn bar given the random variables from S1 to Sn minus 1. When we apply the conditional expectation to this term here, note that if n is less than or equal to J, this is equal to Sn. Otherwise, we have 0. The expectation of 0 is 0. The conditional expectation of Sn given S1 to Sn minus 1 is greater than or equal to Sn minus 1 because process Sn is a submartingale. The conditional expectation of this part here is lower bounded by Sn minus 1 times indicator n less than or equal to J. When we take the conditional expectation of the mth term, note that we are conditioning on S1 all the way to Sn minus 1, and small m, the index of the sum, is from 1 to n minus 1. Sm is one of the random variables we are conditioning on. This means that the conditional expectation is equal to Sm itself. The conditional expectation of Sn bar given S1 to Sn minus 1 is lower bounded by Sn minus 1 times indicator n less than or equal to J plus this sum here. We can write this as summation m from 1 to n minus 2 Sm indicator m equal to J plus Sn minus 1 indicator n minus 1 equal to J. This term and that term can be combined as Sn minus 1 indicator n minus 1 less than or equal to J. This expression here is Sn minus 1 bar. The conditional expectation of Sn bar given the random variables from S1 to Sn minus 1 is the expectation given the random variables from S1 to Sn minus 1 and S1 bar to Sn minus 1 bar. This is greater than or equal to Sn minus 1 bar. We can take the conditional expectation of both sides with respect to S1 to Sn minus 1 given S1 bar to Sn minus 1 bar. Because we are conditioning on Sn minus 1 bar, the conditional expectation of this side is itself Sn minus 1 bar. And by the law of iterated expectations, what we have on the left-hand side becomes the expectation of Sn bar given the random variables from S1 bar to Sn minus 1 bar. If Sn is a submartingale, the sequence Sn bar is a submartingale. Similarly, we can show that if Sn is a martingale, then Sn bar is a martingale. Sn bar is equal to Sn if n is less than or equal to J, and is equal to Sj if n is greater than J. J is a positive integer. It's a stopping time with respect to the sequence Sn. It is always the case that S1 bar is equal to S1. So the expectation of S1 is equal to the expectation of S1 bar. If sequence Sn is a submartingale, sequence Sn bar is a submartingale, and then the expectation of Sn bar is greater than or equal to the expectation of S1 bar. We proved on the first page that if sequence Sn is a submartingale, then the expectation of Sn is greater than or equal to the expectation of Sn minus 1. Now let's examine the conditional expectation of Sn given the random variables from S1 to Sj. We are also conditioning on J. If n is less than or equal to J, Sn is one of the random variables we are conditioning on. The expectation is Sn. If n is strictly greater than j, the conditional expectation is greater than or equal to Sj. Recall that on the second page, we have this property of submartingales, that the conditional expectation of Sn, given the random variables from S1 to Sn minus m, this conditional expectation is greater than or equal to Sn minus m. So here, if n exceeds j, the conditional expectation is greater than or equal to Sj. Let's repeat this investigation for the stopped process, the sequence Sn bar, which is a submartingale if Sn is a submartingale. We have this expectation. Here is how the stopped process is defined. If n is greater than j, Sn bar is equal to Sj. If n is less than or equal to j, Sn bar is equal to Sn. Comparing these two expectations, we obtain that the conditional expectation of Sn bar given j and the random variables from S1 to Sj is less than or equal to the conditional expectation of Sn given j and the random variables from S1 to Sj. Averaging over these random variables, we get that the expectation of Sn bar is less than or equal to the expectation of Sn. Now we can prove Kolmogorov's submartingale inequality. Consider non-negative submartingale Sn. The stopping time j is in the set from 1 to m. There is a threshold value which is a. If S1 is less than a, S2 is less than a, Sk minus 1 is less than a, and Sk is greater than or equal to a, and k is in the range from 1 to m, this means that the process S exceeds the threshold value a for the first time at instant k. In this case, j is equal to k. J is equal to the index value at which the process is greater than or equal to a for the first time. If Sn is less than a for every n in the set from 1 to m, then j is equal to m. If the process remains less than a in value for every small n from 1 to m, then j is equal to m. As defined on the previous page, Sn bar is equal to Sn if n is less than or equal to j, and is equal to Sj if n is greater than j. Suppose that m is equal to 5. S1 is less than a, S2 is less than a, S3 is greater than or equal to a. The threshold is reached for the first time by S3. Then j is equal to 3, S1 bar is equal to S1, S2 bar is equal to S2, S3 bar is equal to S3. The process continues as S4, S5, S6, and so on. The stopped process, on the other hand, will be as follows. S4 bar is equal to S3, S5 bar is equal to S3, S6 bar is equal to S3, and so on. Let's investigate another scenario. S1 is less than a, S2 is less than a, S3 is less than a, S4 is less than a, S5 is less than a. No one of those values is greater than or equal to a. In this case, j is equal to 5. Sn bar is equal to Sn for n equal to 1, 2, 3, 4, and 5. Sn bar for n greater than or equal to 6 is equal to S5. We have a submartingale, S of n. A stopped process is also a submartingale. The stopping time j is a positive integer in the set 1, 2, all the way to m. J is equal to k in the set from 1 to m if Sk is greater than or equal to a, and Sn, n from 1 to k minus 1, is less than a. The event that the maximum of Sn, n from 1 to m, is greater than or equal to a is equivalent to the event that Sj is greater than or equal to a. If Sj is strictly less than a, we know that at all n from 1 to m, Sn is strictly less than a. If Sj is greater than or equal to a, like what happened here, then there is a value of n in the set from 1 to m at which Sn is greater than or equal to a. The equivalence of these two events implies that they have the same probability. The process S is non-negative. We can apply Markov's inequality, given that a is strictly positive. The probability that Sj is greater than or equal to a is upper bounded by the expectation of Sj divided by a. Sj is equal to Sm bar. If the value a is never reached, j is equal to m, and Sm bar is equal to Sm. If the threshold is reached, Sm bar is equal to Sj. It's always the case that Sj is equal to Sm bar. By this argument, the expectation of Sm bar is less than or equal to the expectation of Sm. If Sn is a submartingale, the probability of this event is upper bounded by the expectation of S of m divided by the positive real number A.